All right. Hopefully you guys can hear me. You won't be able to see me, which is probably good anyway because you're not looking at much. John sees dead people. It's too bad. I don't think there's any dead people. All right. We're going to go for it. Maybe. Getting crap again. All right. No, you're way behind me. Oh, this is so frustrating. All right, camera's off. We're going for it. I don't know what you guys are going to see, what you guys are going to hear. If it doesn't work out well, we'll just reschedule another class. We'll do class 5 again, whatever day is the next day after this day. So we're only 18 minutes late. Hopefully we're good. We're going to go for it. All right, online, the chat that you're all using, or some of you are using, just be respectful. This is just a housekeeping item. For people that get distracted by the chat, that can happen. While we're going through all of this material, just close it, and you should be fine. And thank you. Thanks for playing by the rules. We appreciate it. We're gonna move. The mentor program study group, we set that thing up, and it's been really cool to see how many people have been in it and using it. So hopefully you're doing that too. Today we have 555 users on the study group, and I'm not sure if you guys are seeing my slides or not, or if it's just me talking. Is it just me talking? Because if it's just me talking, that's not going to be very fun. You won't be able to see all the pretty pictures and things that I got for you. Audio's good. You hear me. Looks like the slides are pretty far behind. All right. Well, hopefully things are keeping up. This is another thing that this released today. So S2Me version 2 was just released today. We're kind of excited about it. It's not really in general release. It's more in kind of limited release. So what I'd like is anybody who's watching, go out here and take it. Test it out. Tell us what you like, what you don't like. We already have an idea of many of the things that we didn't like necessarily, or we do like. But anyway, go take it. Tell us what you think. We developed this thing because we're trying to reach the normal people. I've told many people before that there's about 1 million information security people in the United States, and by comparison, there's 330-ish million what I call normal people. And we're all in this together, right? They're connected to me. I'm connected to them. We need to figure out ways to build better information security habits in everybody. So that's why we created the S2Me. It's free. It'll always be free. Don't worry about that. Got nothing to sell. Just want your feedback. All right. Before we get into this too much or too deep, let's, I like to do dad jokes. So why did the picture go to jail? If you already got the slides, you already know the answer. This is why. It was framed. Funny. All right. Whatever. I know it's dumb, but I like to loosen things up a little bit before we get into the meaty stuff. So this is where we're at right now. We're through chapters 1, 2, and 3. We're mostly through chapter 4. Today what we're going to cover is we're going to cover the rest of encryption. It gets kind of meaty when we talk about some of this encryption stuff. And then we're going to get into physical security. There's going to be a lot of things to memorize. I'll try to point those things out for you. Then there'll be a lot of that stuff that, you could spend an entire month just on one encryption algorithm if you really wanted to get deep into the math. But we're just going to hit the things that you need to know so that you're well prepared to take the test. And I think a lot of these things you'll be well prepared for in real life too. So there's good stuff here. 166 slides, not too bad. All right, first quiz question. This is going back a couple of classes. What model should you use if you're primarily concerned about confidentiality of information? Brewer Nash, Chinese Wall, BellaPad, Bibba, and Clark Wilson. Now, you know BellaPad and Bibba, if you remember, and you memorize that. Those two are sort of the opposite of each other. The answer here is BellaPad. And I think that's a nice graphic for you that you can use in your studies to understand the properties and of those two models. Should help you in your studies a little bit. And if you think about it, it makes a lot of sense. So in BellaPad, if I'm really concerned about confidentiality of data, I wouldn't want to be able to write top secret data down to the confidential layer, because people that have confidential clearance would then be able to see that data, right? Violating confidentiality. The same goes the other way. We don't want to be able to read up if I'm confidential, if that's my clearance. I certainly don't want to be able to read secret or top secret data. So that makes sense, the no write down, the no read up. Same with BIBA, just sort of the other way around. Right, on Intel x86 systems, the kernel normally runs in which CPU ring? What we're mostly concerned about in information security is, we call it kernel mode and user land. Kernel runs at the lowest layer, the layer closest to the hardware, and that's actually ring 0. So that's the answer, ring 0. This graphic that you see here came from VMware. I know there were some questions about where VMs run. What ring? There's your answer there. You won't probably be tested on that. You'll probably be more tested on where the kernel is, what the kernel's function is. The reference monitor in the kernel will be something that you'll probably see on the exam, and then user land and the kind of the difference and why they segment it out this way. That's all test worthy. Which type of cloud service level would Linux hosting be offered under? So infrastructure as a service, identity as a service, platform as a service, or software as a service. The right answer here is infrastructure as a service, so A. And I think this is also a nice graphic for you to just reference, right? You've heard of many of these products before. Now you can put those products on which platform they are, or what type of platform they are. So it should help you a little bit because it'll give you some real world reference. And this stuff is also testable and something you'll use later. So good stuff. This one we haven't covered yet in class, but if you've read ahead, you already know this, or if you've got some information security experience with these things. Nonrepudiation is best described as what? What nonrepudiation is being able to prove that somebody did something on a system. System integrity becomes really important if I'm going to be, concerned about non-repudiation. Non-repudiation comes into play a lot when we're doing investigations. We need to be able to prove that something happened when it happened. That's why timestamps are really important. That's why log files are really important. In this respect, and what we're going to talk about tonight is how we can use encryption to enforce non-repudiation. The answer here, based on all what I just told you, is A. So proving a user performed a transaction on a system is the correct answer. All right, this is where we're at. Domain 3, Security Engineering, Chapter 4. We're going to finish this one off tonight, which is cool. I'm going to have to move fast, though, because technical issues. All right, here's our agenda. We're going to talk about types of encryption, cryptographic attacks, implementing cryptography, perimeter defenses. This is now talking about physical security. So those first 3 topics are all encryption. Then we're going to shift gears and get into physical security in the last 4 topics: perimeter defenses, site selection, design and configuration, system defenses, environmental controls. That's all physical security. We'll finish this class tonight, and then you can chill out a little bit. You'll have the weekend, and then Brad's going to hit it on Monday, hopefully without any technical issues. I'll take the blame for it because it's usually user error, so we'll just say it was that. I don't know what the problem is because now it shows that I have an excellent connection, but I'm afraid to turn on my video and screw this up more, so we're going to stick with what we got. These were formerly separate domains, so you had 3 domains kind of wrapped up into this one. That's what makes it so long. I'm not sure why they organized it this way, but it is what it is. Starting on page 160. So if you have your book and you're using that for reference and you want to follow along, that's where you could go. All right, so starting off with symmetric encryption, there are two main types of encryption: symmetric encryption, asymmetric encryption, and then you've got hash functions. The hash functions isn't really a cryptographic, it is an algorithm, but it's not. We don't really consider it encryption per se. It really just creates it's a one-way function. You can't go back the other way. But anyway, symmetric and asymmetric encryption are the two types of encryption we're going to talk about. The primary difference between the two is symmetric encryption uses the same key to encrypt and the same key to decrypt. So it's just one key for both. Now that and a number of other things within the math make it much faster and make it much stronger per bit of key. So the length of the key is when I'm talking about per bit of key. Typically, the longer the key, if used in a good algorithm, will produce a stronger encryption. We also call this secret key encryption. When we get to asymmetric, well, it's two different keys. So that's the biggest difference between the two. The big weakness with symmetric encryption is if I'm communicating with somebody who's not close to me, I have to somehow get them the encryption key. Because if I encrypted it, they're going to need that same key to decrypt it. So how do I get it to them? And the way we would do it before DiffieHellman, which we'll talk about tonight too, is you'd have to do it out of band. So maybe you'd send an email with something encrypted, and then call them up potentially with the key. Sometimes keys are translated into just normal characters, normal words. But that's one way you could do it. But that's the biggest weakness with symmetric encryption. Stream and block ciphers, that's just two different modes of how symmetric encryption works. Stream is bit by bit. It doesn't work on blocks of data. Block ciphers work on blocks of data. So if you look at the different block ciphers, probably the two most famous ones would be DES, which is the data encryption standard, 56-bit blocks with the 64-bit key, which we'll get to in a little bit too. And then AES with the advanced encryption standard, which I always get the name pronounced incorrectly. It's Rijndael, RIJN, whatever, you'll see it. That's the actual name of the encryption algorithm. How it's been called the advanced encryption standard is because the federal government approved it. So it's now a federal information processing standard, FIPS standard. But anyway, stream mode, 1 bit at a time. Block mode, chunks of data at a time. That's the important things to remember. So again, symmetric encryption, one key, encrypt, one key, decrypt, fast, strong. Two different modes, stream, 1 bit at a time. Block mode, blocks of data at a time. That's the important part here. One of the things that we have, one of the deficiencies sometimes in an implementation of an encryption algorithm is the predictability of the encryption. Because if I encrypt something with the same key, say two messages, and the messages both start off the same way, if I encrypted it with the same key, those first bits of encryption would be the same. So it would aid in crypt analysis in breaking the encryption to find the message when you have the non-randomness. So the initialization vector is just a random chunk of data that gets added to the encryption algorithm. Now, it's not always added at the beginning. It could be added, it can be used as a feed-in into another round of encryption. But in most cases, the initialization vector, you can think of that as being at the beginning of the encryption functions or method. But that's what the initialization vector is. It's just random data that you insert in. Sometimes we would call that like salt is kind of the same thing with hashing. When we get to hashing, you'll hear salt, kind of the same concept, really. Chaining, so there's two types. When you talk about modes, when you talk about stream mode or block mode, chaining always refers to block mode. Feedback always refers to stream mode. So when you hear the mode of encryption, this comes into play a lot more when we're talking about data encryption standard, which will be on the test. Even though the data encryption standard is no longer supported, I think It's cracked now. Just single key, just DES is cracked in about 26 hours. So nobody uses DES anymore. It's slow. It's weak. But DES has different modes. There's 5 different modes that we're going to talk about tonight. 2 of those are chaining. 2 of those are feedback. So that means 2 of them operate on blocks and 2 of them operate on bits. And then there's one sort of hybrid mode, which we'll need to probably memorize for the test, but then you can forget it afterwards because nobody's using DES anymore. But chaining is just taking one block of encrypted text and feeding it into the next block of encrypted, for the next block of encryption. Feedback is the same thing, just with bits. So this is sort of what the initialization vector looks like. You have the plain text block there, which is balance :2000 with a bracket on the left side. You would feed the initialization vector into that, XOR it. So you see that circle with the plus on, that's an XOR. It's just a function. And if you remember, you'll need to know that XOR table when you take your test. You XOR those 2 together, and then you encrypt it with the key, and then you have your cipher text block. That's the initialization vector. All right, data encryption standard, it's old. It's been around since the 70s, mid-70s, 76. It's actually, the name of the algorithm itself is actually the data encryption algorithm. When it became a standard was when the government approved it and made it a FIPS, right, a Federal Information Processing Standard. And we'll get to the number. I can't remember off the top of my head what number that is, but I think it's on the next slide. Designed by IBM, and it used to be the old Lucifer symmetric cipher. 64-bit blocks, 56-bit key. And you can see just the diagram there. The diagrams always help me a little bit visually, sort of understand, like, what are we talking about? So you can see the 64-bit plain text, the magic box with the DES cipher, and what comes out the other end is a 64-bit cipher text. You'd have to use that same 56-bit key to decrypt it on the other side. So that makes it a symmetric encryption algorithm, obviously. All right, so here are the 5 modes. We'll need to know these. Now, there are a couple things that I'll show you when we get through this, like tables to remember and reference. So if you have your own slides, maybe mark that one as one that you want to go back and sort of memorize. But 5 different modes to encrypt data. They're actually all, there's block mode and then there's stream mode, but truly the way it works, there's FIPS 81, I guess you can see in the bottom. 5 modes: electronic codebook, which is the weakest form, it's the slowest form. Cipher block chaining, cipher feedback. Both of those errors propagate through the encryption algorithm, which means if I encrypt something, these are all feedbacks, or it's either a feedback if it's operating in stream mode, or it's chaining. So you can see that cipher block chaining, that would be working on blocks of data. The cipher feedback and the output feedback both work on bit, right? Bit level. Now the way these work, and you'll see in the diagram, is you encrypt one block or one bit of data. You'll use that then in the next block of data. So when I say errors propagate, if there's an error in the previous block, it's going to propagate throughout the rest of the encryption, and your data will be corrupt. You won't be able to decrypt it. Electronic codebook is the first. So when you look down the list of 5 modes there, it's oldest to newest. So electronic codebook was the oldest form of, or oldest mode of DES. Counter mode is the newest. So that's that. Notice the words, those are always key, right? If you memorize or remember that chaining is working on blocks of data and feedback is working on bits of data based on the previous slides that we had, you'll know sort of how, at least the basics of how these things operate, just, by those names. All right, so here's the first one, the weakest form, electronic codebook. It's also the oldest form, no initialization vector. So this is going to be very susceptible to crypt analysis because we lack the randomness. So if I take 2 messages that are similar or start the same and run them through the encryption, they'll encrypt that first part basically the same way. The first blocks will encrypt the same way. Lack of diffusion, so we don't take the bits and kind of mush them across other blocks. So there's no diffusion, which is also a weakness. Susceptible to replay attacks. Don't see it anymore. I guess it'd have to be a really, really old system if you saw DES still being used in this form. Identical plain text with identical keys will encrypt to identical ciphertext. That makes crypt analysis pretty easy, and that's the replay attack piece. This is just an old story I remember from 2013 where Adobe lost a big bunch of passwords, 153 million passwords or emails, whatever. And they were all encrypted, but instead of doing it the way we would normally do it with a hash, they did it with DES. So this was 2013. They encrypted it with DES, and not just that, but the weakest form of DES, which was, in our industry at the time was just like, what? Why would you do that? So they caught a lot of flack for that. If you know the history of Adobe and information security, you can find a lot of stories about some of the things that Adobe's done over the years. The next mode of encryption for DES is the cipher block chaining. Block mode of DES. XOR is the previous encrypted. This will make a lot more sense when I show you that diagram. But XOR is the previous encrypted block, so it's already been encrypted. It's going to then take that and use that in the next block of plain text to be encrypted. So those errors will propagate throughout the rest of the chain. Chaining destroys patterns, so that means that you won't have the two messages that are similar with the same keys encrypt to the same data. That won't happen with cipher block chaining. The biggest thing to remember about cipher block chaining is that it's slow and errors will propagate. This is the first mode that uses the initialization vector. So you can see the difference between electronic codebook on the left and cipher block chaining on the right. So encrypted electronic codebook, there essentially is no sort of feedback in additional blocks down the line, whereas in cipher block chaining that does happen. The initialization vector is used in the cipher block chaining with the key, and it looks a little confusing because it almost looks like it's a little bit backwards, like plain text should be at the top, but this is how it actually works. So things to remember again about this: errors will propagate. The chaining destroys the patterns. I think that's about all you need to know about cipher block chaining. Cipher feedback. So now there's the word feedback, so you know that this is working on at least stream emulation, if not stream mode. Very similar to cipher block chaining, and you can see the diagram is essentially the same. The difference is we're just working in stream mode. So being that we are working essentially the same with the initialization vector, with the roll into additional blocks of cipher data or encryption, those errors will propagate also with cipher feedback. So you can see in the diagram. I spend more time on the diagrams, honestly, than I do on the words. So that's just a tip that I use. And there you can see the sort of the difference. Now output feedback. Feedback, again, we're working on sort of a stream mode, or at least stream emulation. Previous ciphertext is used for feedback into the next, but the difference you can see is errors won't propagate because of where the XORs are taking place. Do I have the right two there? Where's the diagram I'm looking for? The difference. Oh, we've got the initialization vector at the top. Plain text comes in at the side. So where the plain text comes in and is XORed with the ciphertext, that's what creates the non-propagation of errors. So, and all this stuff, honestly, after you get through the exam, you can forget it, but you will need to memorize these basic things. And I'm going to get to a table. If you just memorize the table, you'll be fine. Counter mode is the newest and was the last mode of the data encryption standard. This didn't use it didn't use previous ciphertext in the next block of ciphertext or anything like that. What it used was a counter and a nonce. So it uses a counter that's a random number that gets generated. Patterns are destroyed, so it won't be susceptible to replay attacks. Errors will not propagate. It's just that's how it works. It's just a counter. It just counts up as you continue to go through different rounds of encryption. This is the table that I told you, and I even put memorize OK question mark there. If you memorize this, you're most of the way there for the test. All right, so there are different types of DES. So those were the different modes of DES. Now we have different types. Single DES is one key, one round, or 16 rounds of encryption. 64-bit blocks, 156-bit key, 16 rounds of encryption. It's the work factor. Work factor is how much work goes into breaking the encryption. The most common way to break encryption for DES would be just to exhaust the key space. So that means you try every combination of characters until you find it. The first time it was sort of broken, I think commercially, was with Copacabana. Took a lot of money, well, $10,000, but a lot of CPUs working together to exhaust that key space and then break encryption or break DES. Today, it's about 26 hours, I think, is the best I've seen. Probably faster now. If you're interested in these things, this is a cool site that you can go to and go use. It's is crack.sh, and so you can take and play around yourself with cracking encryption. There's a lot of fun things you can do with this site. All right, so DES, when that was getting close to being cracked, or about the time it was being cracked, there was sort of a rush to, oh crap, we need to create something new. So they decided they didn't have an algorithm that had been vetted or gone through the right process to be approved as the standard. So what they did is they went through a rush of how can we use the existing encryption algorithm to not be susceptible to cracking anymore. So what they came up with was triple DES, and triple DES became the FIPS standard 46-3. You don't need to memorize probably FIPS 46-3, but you need to memorize, triple DES and why it came about and those things. Now DES itself was already slow, so now triple DES is essentially you're going through the algorithm 3 times. It's even slower and much more complex. So triple DES, although it's still sort of pseudo used, and some people would argue that it's officially still a standard. Why? Why would you use it? Advanced encryption standard is definitely the way to go. There's Twofish and Blowfish, and we'll talk about those. Those are encryption algorithms that Bruce Schneier and his team put together. They were finalists for the advanced encryption standard. Reindel was the one that won. We'll get to that too, but double DES, which is essentially using encrypting it twice with 2 keys. What would happen is if you started on one end with working through the key space and started at the other end, you'd meet in the middle, and that's the meet in the middle attack. So it was essentially the work factor for breaking double DES essentially becomes double that of single DES. So that's why double DES wasn't used. So instead of 26 hours, it'd be 52, still weak. This is the publication. If you're interested in these things, you can go read it. You can really never stop learning about encryption if you really want to get into it in terms of the math that's involved, and it's really cool. And then I think Ryan probably talked about Kirchhoff principle last week. That's in general the secrecy of the encryption algorithm itself should not have any effect on the strength of the encryption, and that's held to be true. All right, so triple DES, this is what it does, 3 times per block. And 46-3, the actual standard for triple DES, is encrypt, decrypt, encrypt. You can either do that with 1 key, which then becomes nothing more than DES, right? Because I'd be encrypting with the key, decrypting with that key, and then encrypting it again. That's just the same as DES. So when you see 1 triple DES EDE, encrypt, decrypt, encrypt, that's it's dumb. There's 2 triple DES, which is using 2 keys, and then 3 triple DES EDE using 3 keys. That would be the strongest. So applying triple DES EDE, so EDE just means encrypt, decrypt, encrypt, with the same key each time, results in the same ciphertext as single DES. 2 triple DES, 1 key to encrypt, key 2 to decrypt, and then key 1 again to encrypt. So it essentially doubles your key strength, which would be 56-bit keys times 2, 112. Yeah, rarely used. The most commonly used is the triple DES with 3 different keys. 168 bits of key strength because I'm using 3 keys: encrypt, decrypt, encrypt again. Sort of the standard until 2030, but I wouldn't use it if you don't have to. It's slow and weaker. So this is just some examples. I think these same examples are in your book about single DES encryption and then triple DES encryption with only 1 key. You end up essentially with the same thing because you encrypted it, you decrypted it, and you encrypted it again. So that's just an example of how the output ends up being the exact same. So you just wasted a bunch of computing resources for no advantage security-wise. The right one is 3-key triple DES EDE. All right, so when that happened, when encryption became essentially broken, the DES became broken, there was a big rush to go out and find a bunch of new encryption algorithms that would work. One of those that came about was IDEA, the International Data Encryption Algorithm. The biggest knock on this one is it's patented. So it means if you use it without abiding by the patent, it's patent infringement. Well, that really, really hindered its adoption. So, I've never seen it used, and I doubt it will. Uses 128-bit key, 64-bit block size. It has held up to Crypt Analysis, so it hasn't been broken. Patent encumbrance is definitely the biggest knock on it. It is slow compared to Rindall or even Blowfish and Twofish and even RC4, 6. So it's slow. But what you need to remember, if you memorize nothing more than what's on this slide about IDEA, you're cool. You don't have to go deep. So then there was a competition that was held after DES was cracked, where people were invited to submit encryption algorithms as a replacement for DES. And they were going to call it, and they did call it, the Advanced Encryption Standard. Currently, it's a symmetric block cipher. It's in FIPS 197 if you're interested in reading those things. FIPS, again, Federal Information Processing Standard. There's a ton of FIPS out there that you can read. Not all of them are related to encryption. FIPS 199, for instance, is about classification of systems for FISMA compliance. But that's one FIPS that you could read. Uses 128-bit, so 10 rounds of encryption if you're using a 128-bit key. If you're using a 192-bit key, 12 rounds, 256-bit key, 14 rounds, and then encrypts 128-bit blocks of data. I'd love to tell you that you don't have to memorize that, but you probably do. But then you can probably forget it afterwards because rarely do we spend that much time unless you're doing this regularly. It's an open algorithm, free to use, free of any intellectual property. You can actually look at the algorithm itself. It's all open source, designed to replace DES. This was the competition that was held. So you can see RC6 was in the competition, Serpent, Twofish. You can see Bruce Schneier's name as one of the authors for Twofish. I've always had a ton of respect for Bruce Schneier. The best book ever on encryption, if you want to read it, kind of an introductory book, is Applied Cryptography. It's a red book written by Bruce Schneier. It's a great book, great introduction to encryption. But we had Mars, 11 authors there, RSA, so Revest. Usually when you see RSA, you think of Revest, Shamir, and Adelman. That's the RSA. But here, Shamir and Adelman were not part of RC6, but Revest was. Rindall, those are the 2 authors there, and Serpent. At the end of the day, who won the competition was Rindall. yeah, that's how it came about, to become the standard. All right, so this is how it works. This is just the basics of how AES works. 4 functions run in order: SubBytes, shift rows, mix columns. So shift rows, you can think right there that's shifting rows. If you're talking about a block of data, and you can think of it as like a Rubik's Cube almost, just the face of a Rubik's Cube. 4 rows of 4 16-byte blocks. Shifting rows is just taking those rows, right? If you got 4 by 4, you got rows and columns. Shifting rows is just shifting those rows, over. Mixing columns, so it all makes sense. And when you look at the pictures, they also make sense. So first is SubBytes. That's a confusion function. It just substitutes bytes. Takes a byte over here, puts it over there, and vice versa. The bytes are substituted according to a substitution table called the S box. So if you hear S box, you hear confusion, you hear AES, what's the first function? It's SubBytes. If you hear any of those things, that's good enough for the exam. So hopefully that makes sense. It's going to be a lot of memorization. I get that. Again, I like the diagrams because then it helps make sense to me. SubBytes, confusion, AES, the first function, then you're good. If you're S-box too, that's part of it. Shift rows, so just shifting rows, right? You can see how the rows just shift over, and you started on the left, and then now it looks like the right because you shifted the rows. That's a diffusion function. If you remember when we first started, I think Ryan talked about confusion, diffusion as being 2 sort of important functions in encryption. This is a diffusion function. Yeah, that's good enough for that. Mixing columns, so instead of the mix rows, we're mixing columns. Same sort of thing happens. It's diffusion. Now the mixing of the columns is, if you're into math, you might geek out about finite field mathematics. You don't need to know finite field mathematics to pass the exam or to be a security person, but it's the state, and that's essentially the math that's used for this function. And then the final function applied in each round. So again, 10 rounds, 12 rounds, 14 rounds, depending on the strength. This is the final function. XORs the state with the subkey. The subkey is derived from the key itself, so it's basically a portion of the key that's then XORed with what you created through all the other stuff, right? So you've done all those other 3 functions. The AddRound key just adds a part of the key XORed with your final state that you had in the first 3 functions. That's the last function in AES. That's the AddRound key. All right, this was Bluefish and Twofish. These were the ones Bruce Schneier and his team submitted. The only one that made it to the final was the Twofish, but Blowfish was also submitted. Yeah, good encryption algorithms. You can go use them today. They're still out there, and you can read about them and all that other stuff. It's just not the advanced encryption standard. Blowfish, 32 through 448 bit, so it's a variable key length. Default is 128. Works on 64 bits of data, though, so it's a block symmetric algorithm. Twofish was the AAS finalist. 128-bit blocks, 128-bit through 256-bit keys. Both are open, patented, freely available. You can go find Blowfish here. This is, and it is implemented in a number of products. So if you're interested in these things, and then that's a picture of Bruce. Then, that's Twofish. Same thing. If you want to go get a copy of it, you don't need to know that for the exam. I just put it there more for reference if you like geeking out about those things. All right, RC6 was a finalist. RC5 was not. But these were both written by the same authors, and the R was Revest. Symmetric Block Cipher by RSA. 32-bit keys for testing in RC5, but when it's actual in operation and a replacement for DES, it's 64-bit keys. That one was not ever going to make it really to the finalists because It was really written more to be a replacement for DES than it was to be an actual, long-term use. Key size ranges from 0 to 2040 bits. RC6 was the AES finalist, or the Advanced Encryption Standard finalist, based on RC5, but it kind of beefed up for it. Stronger. That's that. All right, so we got through symmetric encryption. I know that's a lot, and you could go so much deeper and so much more, but those are the real basics, and those are the things that will be tested on. Encryption is just a fascinating, or cryptology. If you remember back with Ryan's kind of introduction, cryptology is the study of, cryptography. If you're into that stuff, it's super cool. And if you're new to it, start with that book by Bruce Schneier, Applied Cryptography. Great place to start. All right, so now we're going to get into asymmetric encryption. It's fun. We'll get into it. So DiffieHellman, so one of the problems we had, so this is a key exchange protocol. One of the problems we had with the symmetric, if you remember, was exchanging keys. Same key to encrypt as we use to decrypt. How are we going to get the key from one place to another? DiffieHellman created this key exchange protocol to do that, and it's an asymmetric encryption algorithm. So created it in 76. Now, if you remember DES came out in 76, so the timing was really good. RSA algorithm. RSA is a different algorithm. It's not a key exchange protocol or algorithm, but RSA is an asymmetric encryption algorithm invented in 77. It's one of the first asymmetric encryption algorithms. Now, the reason why I'd use an asymmetric encryption algorithm is because I don't have to share keys. It makes for commerce really easily, right? When I'm using, TLS or used to be SSL, it makes that key exchange much better, so I can do commerce without having to exchange keys first. What typically happens with asymmetric encryption algorithms, due to its slowness and its weakness, is we would use the asymmetric encryption algorithm to then agree upon or exchange symmetric keys and then continue the rest of our conversation using the symmetric keys. That's the best way to sort of architect this. But asymmetric algorithms, 2 keys, 1 key to encrypt, a different key, but a derived key to decrypt. And the same works the other way. A lot of times we hear about the private key pair. It's a private key and a public key. You give the public key out to everybody you want to. If I encrypt something with my private key, it takes the public key to decrypt it. So there's some proof that I am the person I said I am, especially when I plug certificates into it. A certificate is just basically vouching that I am the proper owner of that private key, and I've sort of been vetted. But if I encrypt something with my private key, you give the public key out to everybody, so that means that everybody could decrypt what I encrypted. And the reason why I would do that potentially is to sort of justify that I am who I said I am. Now, the other way also works. If somebody wants to send me something secret, they can encrypt it with my public key, and only I have the private key, so only I would be able to decrypt that. That's some of the basics around asymmetric encryption. So the math behind asymmetric encryption, and you only need to remember, factoring large prime numbers and discrete logarithms. Those are only 2 functions that you need to sort of just know the basics about. Other than that, you won't have to get into any more math. But those are one-way functions. Easy to compute one way, very difficult to get it the other way. Not impossible, just really difficult. And this is just, if you like diagrams, you don't have to memorize this. And this particular picture isn't going to be on the exam, but it helps to sort of explain what I tried to explain to you. Yeah, and the guy on the right, if you look at the picture, the guy on the right, that's Whitfield Diffie. He's still around. I think Hellman is too, but Diffie's been out in the public a lot more than others. He's got like a white hair now, and he's all old. All right, so here are the 2 primary functions, the factoring prime number. So this is when I factor 2 really, really, really big prime numbers and create another big number out of that. That's easy to do it one way, it's really difficult to reverse it. So if I gave you like a super long number and said, this is divisible by what two prime numbers, that's hard math to figure out. Not impossible, but really hard. Doing it, the first way, if I give you two prime numbers and you create the big number, that's easy. But that's really the basis around this form of asymmetric encryption. So factoring a composite number into its primes, the prime number is evenly divisible by only one in itself if you don't know what a prime number is. So 3 is a prime number, 5 is a prime number, 7 is a prime number. It's just they're only divisible by itself and 1, right? So you can't divide it into other numbers. Composite number is evenly divisible by numbers other than one in itself. So that's the composite. That's when if I take two big, really big primes and create a composite number out of that, that's easy math. Like I said, it's hard to do it the other way. And there's just an example in the 4th bullet point about what I'm talking about. The problem is called factoring. No real shortcut, but you can work through the math. You just essentially have to go through all the key space. Just try one after another until you get it. But other than that, there's no other shortcut around it. It's the basis for RSA. Factoring large composite numbers, thousands of bits long, is really difficult one way, hard to do it the other way. So the one that I would expose would be the composite number. That would be essentially the public key. It's really hard to derive the private key that created it or that was derived from it. That's how they get married together. That's the private public key pair. It's really hard to do it the other way. But that's essentially how it's used. You would share that big composite number as the public key. The other way to do it is the other common asymmetric encryption method is the discrete logarithm, and that's just exponentiation. So if you take, there's an example there in the second bullet, 7 to the 13th power, it gives you 96,889,010,407. So if you do it that way, that's easy, 7 to the 13th. But then if you ask the question, that number, the large number that's the exponent, or what's been, I guess, exponent. What's the exponent of that number divided, or into 7, or 7 into that? So that's much more difficult working it the other way, right? So one is factoring the prime numbers, and the other is just this discrete algorithm problem. This is the basis for DiffieHellman, El-Gamal, which never really became super popular. It's actually a pretty good algorithm, but it's still out there too. But El-Gamal is another asymmetric algorithm. The basis for those two that you'll hear today. So most of them are factoring prime numbers. All right, so here's Diffie-Hellman, the key agreement protocol. Two parties, they agree on a symmetric key, and it's just an exchange back and forth using public-private key pairs, but also using that discrete logarithm. Elliptic curve cryptography is a discrete logarithm that's applied, plotted or applied to an elliptic curve. It's really strong. It's really fast. It just never really, it's still used, in many places. Just never really caught on like the others. So it's taking the discrete logarithm and then doing something more with it, applying it to an elliptic curve, which that's what makes it stronger. If you just had the discrete logarithm and didn't apply it to the elliptic curve, it'd be the same. But it's pretty strong, and it's all math. Less computational resources, so it worked in lower power devices more than some of the other asymmetric encryption algorithms, because asymmetric itself is slower, and it takes more computing power than just a symmetric encryption algorithm. So having less computational resources, less resources for the computer, used to be a much bigger deal than it is, kind of today. All right, so here's some trade-offs. This just explains the difference between, in terms of strength and key length, for the two different types of encryption, so symmetric versus asymmetric. And you also have the factoring prime numbers and the discrete logarithm equivalent key strengths to get the equivalent encryption strength. So you can see that 112. Let's take 128-bit AES advanced encryption standard, encrypted data, you would need an equivalent of a 3072-bit discrete logarithm key. And so, just kind of gives you an idea. But it also, you can see in this table how much stronger elliptic curve cryptography is versus the other two forms, such as RSA for factoring prime numbers or Elgamal for discrete logarithm, by almost by a factor of 10. So it's almost 10 times stronger. Things to remember, from this slide, I think that the table is, it's good information, but the bullet points are really the key. Understanding that asymmetric encryption is a lot slower, it's a lot weaker. And they're typically used together. I think, I already mentioned that, where we would use asymmetric encryption to kind of establish a secure channel, so then we could exchange keys. All right, so that's all you need to know for now between asymmetric and symmetric encryption algorithms. A lot of stuff, I know, but man, we saved you from a boatload more, that's for sure. Hash functions are important. We use hash functions for all kinds of things. Normally we use hash functions. I think the most common places to use hash functions is storing passwords. We don't store passwords, or at least you're not supposed to. Instead, what you do is you store the hash. We also use hash functions a lot in investigations, forensics. We'll create a hash. I think we already mentioned that in a previous class. We would use a hash of maybe a drive or a file just to validate that it hadn't changed. So the way hash functions work, it's just a one-way function. So you put in variable length data on one side of the function. What comes out is always a fixed length result, and that's called the hash. And the hash is always the same. So like SHA, for instance, it's always a 168-bit hash. That's how big the hash data is. I could put a 5 gigabyte drive through the SHA hash encryption, through the SHA hash function, and always come out with a 160-bit hash of that drive. It works one way, so you can't derive, the data that was hashed from the hash itself. Now, where this works really well is two different inputs shouldn't create the same hash result. When that does happen, that's called a collision, and it's a weakness in hash functions in general. So where this works really good with passwords is if I type my password, it goes through a hash, and you store the hash, you can't get my password from that hash. So you never disclose my password if somebody hacked in and stole that password database. And every time I type in my password, it will always hash to the same number. That's how you get validated. If somebody else typed in a different password, it would hash to a different value, and therefore I wouldn't be authenticated. Hopefully that makes sense, but that's one of the most common ways that we use hashes. One-way hash functions, no way to reverse the encryption. Variable length plain text, so my example, a 5 gig drive, well, using SHA-1 will hash to a 160-bit hash value. Primarily used to provide integrity. So I mentioned in forensics we would use this, often. If the hash of the plaintext changes, the plaintext itself changes. That's the theory. When that's not possibly true, is when there's a collision. Some hash functions are more susceptible to collisions than others. Like MD5 is pretty susceptible to collision, so it's not used much anymore. Surprisingly, it's still used often, more often than I think makes sense. In forensics, it's still kind of a de facto, but SHA-1, there's actually SHA-2 and there's SHA-3 now. So in SHA, all the secure hash algorithms, anytime you see SHA, that's an approved standard. It has a FIPS associated with it. So all the SHAs, secure hash algorithm 1, 2, and 3, are all FIPS standards. MD5, not anymore. So hopefully that all makes sense. Newer alternatives, SHA-2 and even SHA-3 is out. So this is what I was talking about with collisions. When different data, different plain text hashes to the same value, that's called a collision. It's a weakness in the hash function itself. And it's bound to happen, right? If there's only 60 bits of hash space, and seemingly infinite plain text space, you're going to always have some susceptibility to collisions. It might be a really small, probability, but it's always going to be there. All right, so MD5, Ron Rivest. So you'll see Ron Rivest's name over and over and over again. He's definitely a pioneer in our industry. He is the same R in RSA. Creates a 128-bit hash value based on any input length. Weaknesses, it's susceptible to collisions, is its biggest weakness in a practical amount of time. Now, practical amount of time just means, really when you take like a work factor, the way I would define like a work factor is if it takes me longer to decrypt or break whatever algorithm, whatever protection you have in place, if it takes longer than what the data value is worth or the shelf life of the data, the work factor exceeds the value of the data, and so it's not worth it. You sort of want to keep above that, right? So if I have data that's only valid for 24 hours, you could use DES then for that. I wouldn't, but you could if the work factor is 26 hours. But that, hopefully that makes sense. MD6 is the newest version of the MD family, first published in 2008. It's not really that new anymore. Not really used that much anymore either. But MD5 was super popular when it was kind of out more. Now SHA, these are a series of hash algorithms. They're all, associated with a FIPS. So you see SHA-1, FIPS 180, -1, 160-bit hash value. So comparing that to MD5, the hash value is longer. That alone would make it probably less susceptible to collisions because you have more key space to fit things into. SHA-2 is recommended over SHA-1 or MD5. SHA-3 was announced and it's finalized. FIPS 202. Now for the test, I don't think you'll get asked if SHA-3 has been finalized or not. It has been. Hvala is another hash function. This is hashes of variable lengths, not just any length. They have to fit within these digests. A digest is essentially the same as a hash value, right? A message digest is the hash value. So 128, 160, 192, 224, 256, 3, 4, or 5 rounds. That's Hvala. Definitely similar to MD5, faster. I haven't seen it used in many, many years. So I don't think anybody's using Hvala, but you could. These are, I don't know, this is what app? The app I used to use, oh my God, I can't remember the name. There's an app I used to use all the time for. But this is Compute Hash. This is just an app where you can create a hash and play around with hash values. Cane Enable. That's been around forever, right? It's a tool, free to use. Don't put it on your computer if it's a work computer, you don't have authorization. But it's a cool little tool to play around with. You can do art poisoning with that tool too, which that'll make more sense probably next week. But it also has part of that program you can compute hash values, which is sort of cool to play with. All right, cryptographic attacks. Crypt analysis is the same as trying to recover, either recover the plain text without the key or recover the key, which then would allow you to recover the plain text. The ultimate goal is probably to recover the plain text. Unless you want to continually do it, then you'd want to get the key. But either way, that's all going to be crypt analysis. That's the focus. So brute force is one way. Brute force will always work for sure if you have enough time and enough computing power. In some cases, you would need thousands and thousands of years. So if you have that much time, then a brute force attack will always work for you, because you'll go through the entire key space with every possible key until you get it. This is, the work factor of 26 hours for DES. This is a brute force attack. It'll always work, but it's just going to take you forever. Other types of attacks, known plain text. This is where I'm recovering or analyzing or researching matching plain text and ciphertext pair. And what I'm trying to figure out, or what you're trying to figure out, is what the key is that sort of made all that happen. So you'll have a matching plain text with a matching ciphertext, right? So you'll have the plain text, and then you're trying to figure out the stuff that happened in the middle to try to figure out that key. That's known plain text attacks. Probably testable. So memorizing these different types of attacks is probably in your best interest. The next one is chosen plain text. This is really, and then you adapt. So these are two very, very similar. They're two different types of attacks, chosen plain text and adaptive chosen plain text, but super familiar or super similar to each other. The crypt analysis, so what you'll have is you'll have the plain text to be encrypted, and you'll just continue to run until you figure out, try to figure out, derive what the key is. Adaptive is, so you'll look at the plain text, and then you'll probably look at the encrypted text too and try to figure out some things that happen. The adaptive is you'll continue to make changes. So you'll make small incremental changes to the plain text to try to figure out what the pattern is on the other side. The neither one of these attacks, known plain text or chosen plain text, AES would not be susceptible to either one of these because of the diffusion and confusion and the multiple rounds. But in other encryption algorithms, I suppose. Chosen ciphertext and chosen and adaptive chosen ciphertext are the same as chosen plain text and adaptive chosen plain text, just the other way. So you'll get to choose. The crypt analysis chooses which ciphertext that they want to try to decrypt, and they're trying to figure out what was derived. This would be, you wouldn't see this in a symmetric encryption algorithm attack because the key space is too. It's just not going to happen going the other way. Usually this would be asymmetric crypto. So like if I was given, like I said in the discrete logarithm or factoring prime numbers, if you give me the huge composite number, try to work that back, that would be, sort of similar to this chosen ciphertext or adaptive. Adaptive means you just change, in multiple attempts or rounds. The meet and middle attack is you start, on one side, encrypting on one side, decrypting on the other side, and you meet in the middle. This is the attack against double DES. These are the different types of attacks. Now, known key seems sort of funky, right? Because if I already know the key, then I already know the key. But this is trying to get a different key. So you have a known key, and you're trying to run through the encryption algorithm. And you're just trying to find either another key or figure out more about how the encryption algorithm works so that in future attempts you'll be more successful. Differential crypt analysis, just looking at different plain texts that were encrypted, and then so you can also adapt those. You can have an adaptive, differential crypt analysis, but you're just looking for mathematical factual changes between plain texts that were encrypted to try to derive the key is differential cryptanalysis. Linear cryptanalysis, you'd have lots and lots of plain text ciphertext pairs using the same key, and you're trying to derive the key. So could be gigabytes of data or more, terabytes even, trying to figure out what the patterns are between I have the plain text, I have the ciphertext, and they're paired, right? So I know that this ciphertext came from this plain text, and I'm trying to figure out that key in the middle. It's just a form of study for that. Side channel attacks aren't actually attacking the encryption itself. They're attacking things like CPU cycles, voltage, fluctuations, things like that to try to figure out potentially how to break the crypto system. Yeah, that would be hard. Other attacks, birthday attacks. So this is the paradox, and people kind of get it wrong because they think. So the paradox is based on if I have 23 people in a room, the odds are greater than 50% that two of those people, two of the 23, will share the same birthday. So using that math and applying that to Crypt Analysis gets you some kind of a head start on things. Where people get it sort of wrong is they think, if I take one person, that means there's a 50% chance that one of these other 22 will have the same birthday. That's not the paradox. The paradox is in the room, in the population of 23, there will be two that share the same birthday. So this is usually, it's always used in trying to figure out hash collisions. And then key clustering. Different symmetric keys applied to the same plain text. They produce different ciphertext. That's just key clustering. All right. Now we're going to apply some of this stuff that we already learned around asymmetric encryption. And we're going now to that last question we had about non-repudiation. One way to do this, so digital signatures, essentially proving that two things. The signature or the file that was signed did not change. That's one thing. And then the second thing is that it was signed by me. So that's going to require at least two functions in order to do a digital signature. So authentication of the identity, so I am the one who actually signed it, and that it didn't change from the time it got from me to you, that's a digital signature. So you'll create a hash of the plain text and then sign it with your private key. So the hash proves that the file didn't change. Me signing it with my private key, assuming that it hasn't been compromised, proves to anybody with the public key that I'm the one who signed it. That's a digital signature. And that's how it works. So this is, just a graph of the same thing. So you have the data on the left, you create the hash. The hash then is signed with your private key. And you got the certificates on the left. Certificate is just essentially a vouching that you are the proper owner of the private key. So when you put, public key encryption or infrastructure, PKI involved, there's usually a third party who validates your private public key pair, essentially. But that's a digital signature. That's what you'll need to know. HMAC is the same thing. Here we had asymmetric encryption that was used, so we had public-private key pair. HMAC is essentially the same thing, except for we're using symmetric encryption algorithm. DES, AES, it doesn't really matter. But so you're combining the same thing. Now, it's not really a digital signature because I've essentially hashed it, and I encrypted it with a symmetric encryption key, I guess, and you decrypted it. It's assuming that nobody else compromised our keys, then I guess it could be non-repudiation, and it could be a signature, but it's not truly a signature, so they call it an HMAC instead. All right, so PKI, I just mentioned it briefly. Public key infrastructure, you don't need to know the details of the architecture of PKI, but you do need to know these basics. 3 forms of encryption are used. Hashing, asymmetric, and symmetric encryption are all used in the public key infrastructure. Essentially, a digital certificate is the public key signed with a digital signature of typically, you could set up your own PKI, but it's got, at the root of the PKI has to be something or somebody that you trust, because they're essentially vouching for the certificate, right? The public key signed with their digital signature, vouching that you are, and that this whole thing, the whole infrastructure is, integrity is there. So a lot of times you'll go, like if you're, setting up HTTPS or TLS 1.3 on a web server somewhere, you'll need a certificate. You can either derive your own, or you can go to a public certificate authority, and they'll issue you one. Now, the advantage of having a public certificate authority is you have a third party who's vouching for it. If you create your own certificate and somebody who doesn't necessarily know you or trust you uses your system, they're going to get, their certificate's invalid. They'll get an error because it's not in their certificate store, and you'll have to sort of deal with that. Poor configuration, probably. But the PKI is essentially that whole infrastructure of support of trust in the integrity of the certificate, the public keys, and the private keys, all kind of being used together. The standard digital certificate format is just a format of the actual certificate, how it's built. It's built off the X.509 standard, which has been around kind of forever. If you memorize just this slide, you're probably going to be fine for PKI. And this slide, sorry. Certificate authorities, I mentioned before that you can either have a private, so companies all the time set up their own PKI because they don't want to go through the expense. They don't need the third-party validation of their certificates, so they'll set up their own PKI. They just want, essentially internal trust between systems. They could set up their own certificate authority. It's just that central authority that authenticates the identity of whoever it is that's you're asking for a certificate, and then just creates those certificates and the private public key pairs, which are all associated together. Certificate revocation list, there becomes times when a private key has been compromised, or somebody who was trusted is no longer trusted, or maybe it was issued an error. Certificate authorities will keep a certificate revocation list, which is essentially a list of all the certificates that have been revoked. IPsec, we're going to hit IPsec twice, so don't worry too much about getting it all now. IPsec is just IP security. IP version 4 was never built with security in it. It was never built with security even in mind. It was all built with resilience in mind. So there's no real confidentiality built into IP version 4. There's some integrity in TCP, but overall there's no security. So when we needed to implement some security for this, IPsec sort of came about. It's built into IP version 6, so it's not really an add-on to IP version 6, but it is an add-on to IP version 4. One of the methods used for providing virtual private networks, there's lots of different types of virtual private networks. One of the most popular is IPsec. 2 primary protocols, so it's a suite of protocols. Protocols is just essentially think of a protocol as a language or a method of doing something over and over and over again the same way. 2 primary protocols for IPsec, authentication header and encapsulating security payload. You can use them both together, but they serve different functions. Authentication header essentially validates that this packet is a valid packet. It's authenticated. Encapsulating security payload actually encrypts parts of the data. So 2 different protocols, but they very often work together. There's other protocols in that protocol suite. Those are the 2 primary protocols, but other protocols in the suite, Internet Security Association and Key Management Protocol, ISACAMP, we would call it, and Internet Key Exchange are 2 different protocols. And what these protocols are typically used for is they're used for negotiation and setting up sessions, setting up parameters on how 2 systems will communicate with each other. Those are their primary functions. They don't really protect the data per se. They do more sort of authentication and session setup, teardown kind of stuff. Authentication header provides authentication and integrity for each packet, so the packet hasn't changed from one point to another. When I say packet, this is data that's transferred over a network. We're going to get more into networking, and that's why we'll get more into IPsec again when we next week when we start getting into networking a little bit. We don't have to go deep into networking, so don't get freaked out at all about that. We'll go through the basics because that's what you'll need for the test. So authentication header, authentication and integrity for each packet, no confidentiality, so there's no encryption involved of the actual data. It's just essentially a digital signature for the data. Protects against replay attacks. So if an attacker, a man in the middle, captures packets and replays them, that's probably not going to be as successful with AH involved. Yeah, and then encapsulating security payload does do the encryption of the actual packet. That's what it looks like. You can see the top one is just authentication header. So after the IP header, it comes the authentication header, and then the TCP, and then the actual data. These are all just headers. And when we get to next week, we'll talk about encapsulation, how data or how these headers are added to the data as it goes down, essentially down the stack of a computer. It's really kind of, I mean, when you think about it, it's all very, very logical. So it'll make sense. And then you can see that the ESP, when we add encapsulating security payload, it has its own header. So in that packet on the bottom, there is no authentication header. It's all just ESP, but we've encrypted the data. Security Association and ISACamp. Security Association, simplex. So simplex and duplex. Simplex is one way, duplex is two ways. So you can think of simplex as being like me doing a walkie-talkie, right? I push the button and I talk. It's a one-way communication. What you'll do back to me will be another one-way communication. That's simplex. When we're sitting here talking together, person to person, that's duplex communication. There's communication going on both ways at the same time, sort of thing. That's sort of the difference. So simplex means it's a one-way, and then you'd have a one-way back. Two systems communicating via ESP will use two security associations, one in each direction. And that essentially tells each of the systems sort of how to use this data. 32-bit, you don't need to worry about that right now. Security parameter index, we're going to cover that again next week. And we'll get into ISACamp a lot more, too, next week. Tunnel and transport mode. So we had those two primary protocols, authentication header and encapsulating security payload. We have the supporting protocols, primarily ISACamp and hello, brain fart. But then now there's two modes, right? Tunnel and transport mode. Tunnel mode essentially sets up and it uses essentially authentication header, encapsulating security payload to set up a tunnel. So it's like a private communication. You can't really get into it, the private communication. Transport mode is essentially encrypting all the data. Two different modes used by ESP. Again, don't worry about it so much tonight, but next week we'll hit it again. This is just what that data looks like. So I like diagrams. I like visuals. I like to understand where this stuff fits. This will become a lot more. If it doesn't make sense now, it'll make a lot more sense next week. I do promise that. But this is just sort of an introduction to it. But you need to memorize it. IKE, Internet Key Exchange, is one of those other supporting protocols for IPsec. Different encryption algorithms depending upon what gets negotiated during IKE. Because DES or IPsec, what it'll do is it'll use the highest, strongest encryption algorithm first. If one supports AES and the other one only supports triple DES, they're going to negotiate to triple DES unless you've set it up explicitly not to permit that. But there's this negotiation that takes place between the two systems that want to communicate. IKE does all of that for the two. All right, SSL and TLS. SSL is been replaced by TLS. The current version of TLS is TLS 1.3. They just continue to sort of update it as sort of technology and I think attacks catch up. So SSL provides the confidentiality for web traffic. This is a negotiated connection again. And HTTPS is a different. HTTPS uses SSL or TLS, but HTTPS is different. It's a different protocol that uses one of these two sort of encryption methods or standards. I don't know if any of you remember Netscape, but that was back in the day. Netscape used to rule the browser world. Where they kind of screwed up is you'd have to pay for their browser, and Microsoft made it free, IE. So that was kind of the end of Netscape. They're still around, but it's just not the same thing. But anyway, you can see the connection that takes place when you connect to a website like this one. ISC2.org. The data is encrypted. It's true because there's that key negotiation that takes place. So it starts off as an exchange of public and private keys. Actually, it's an exchange. You connect. The ISC2 will send you the key, or send you the start of the negotiation encrypted with its private key. So you would be able to get the public key because anybody can get the public key. And that would start the process of setting up the asymmetric encryption session, essentially between the two entities, and then a symmetric key would be negotiated and sent through that encryption, and then the rest of the session just ends up being symmetric because it's faster and computes better and it's stronger. All right, so SSL deprecated TLS 1.3 current in RFC. I don't know if we've mentioned RFCs here before. Yeah, we did. RFCs are requests for comments. 8446 is the RFC for this one. RFCs essentially govern the internet. Other encryption, so PGP. This was Phil Zimmerman. PGP is also still around. This doesn't use keys the same way. It uses what's called a web of trust model. So it just exchanges. There's no central certificate authority. Everybody sort of keeps their own. And then if somebody, in the web of trust becomes untrusted, it gets sort of revoked on everybody's own sort of central, everybody's own sort of list of certificates that they trust. So PGP, still around. This is probably good enough for the exam. SMIME, Secure MIME, Multipurpose Internet Mail Extensions, uses PKI. So we've got, what we talked about with PKI. So we've got digital certificates, asymmetric encryption, and is used to secure emails. SMIME is also still around. Encryption can be done, sort of anywhere in this exchange of mail, typically done both places. So, but if the mail server is doing all the encryption and as the client, I'm not doing any encryption, that would be just an SMIME gateway. But think of SMIME as being an encryption to protect email, and they'd be fine using PKI. Escrowed encryption. So this is you essentially take a key, cut it in half, give one to one party and one to another party. They're held in escrow. And then if something, whatever event triggers the legal requirements of the contract, they release those from escrow, and then you'd be able to use that private key. That's escrowed encryption, and it's used. Clipper chip. This was a bad thing that the United States tried to do. We were a little more concerned about privacy in the 90s. I think nowadays you might even be able to get escrow Clipper chip through. People just don't seem to be as concerned about privacy. But the technology was escrowed encryption standard. It was a proprietary standard. In 93, the U.S. government said that they were going to use this escrowed encryption for telecom devices. The media got no. People got in an uproar, all kinds of whatever. Abandoned in 96. It used an algorithm called skipjack. So if you hear skipjack, think of Clipper chip. Symmetric cipher, 80-bit key. Originally classified as secret, no longer. You can go look at it if you want to. But this didn't work out very well. Steganography. Steganography isn't really encryption at all. It's just hidden communication. You never know that the communication is even taking place in steganography. You would hide a message maybe in a bit, the third bit of each file, or, something to hide the fact that's happening. A lot of times in pictures, you can hide pixels. You can hide messages there. But steganography is essentially hiding the existence of a message. And there's just an example. The vessel image is, the starting image. You would embed your whatever data you wanted to embed, and then you'd have a stego image. To the human eye, you can't tell the difference. Hash values would definitely be different. File sizes would also be different. There's lots of ways to find it, but if you're not looking for it, a lot of times these things go unnoticed. Digital watermarks. More ways. Digital watermarks were used to encode data into a file. So, and you would do this to essentially control distribution of files. You wouldn't really stop the distribution of the file, but you'd be able to determine where that file came from. That's what digital watermarks are used for. And there's a good story there in your book and a good story here about how they did this with, there were leaks of DVDs from the Academy of Motion Picture Arts and Sciences, and they couldn't figure out who was leaking them. So then they started digital watermarking, and then they were able to find, track that down. That's one example where you could use a digital watermark. Holy buckets. All right, 7:42, 18 minutes to get through physical security, but you got to cut me some slack because I was 18 minutes late maybe. But we're done with encryption. A lot of stuff. I wish I could say sorry, but I'm not really, because you got to get through it. It's just a lot of memorization, It's just how a lot of this works, but stick with it. The first time through, it may not make sense. Second time may not make sense. Third time, maybe it starts to sink in. That's all legit. All right, physical security. We definitely have some things to memorize here. Physical security is an often overlooked part of information security. Can't do it because it's part of it, right? It doesn't matter how good your firewall works if I can steal your server. That's the common saying. All right, so things about physical security that are important for us, man traps. So a man trap uses two different controls. One control to get into the man trap and one control to get out the other side of the man trap, or even out the same way, potentially. It's a preventative physical control with two doors, one door on one side, one door on the other, and in between is the man trap. The theory there is if you somehow got in through one door, you'd be stuck in the man trap to allow for a response. Bollards are big things that people put in the ground to stop vehicle traffic. Sometimes they're big metal posts that are sunk 4 to 6 to 8 feet down. Sometimes they're the big balls like you got at Target, right? Those are all bollards. They stop cars, stop vehicles from hitting buildings or entering buildings. Not a lot of times they'll use environmental designs like hills, like concrete benches, things like that. If you want to see a really good place here in Minnesota, if you go downtown Minneapolis and you go to the Federal Reserve building, you'll see some cool kind of environmental design things and how they protect that building from getting bombed or whatever. Smart cards always have a chip on it. They always have an integrated circuit. That's what makes them smart. Different ways smart cards can work. They can either be powered from an external source or they can carry their own power supply. We'll talk more about smart cards, but the important thing about a smart card is it has to have something on it that's smart. That would be your integrated circuit. Tailgating is essentially entering a building, with somebody else's credentials. So you followed behind somebody. It's one of our favorite ways to get into places when we're doing physical, maybe physical social engineering type of attacks is just, tailgating. All right, for the exam, human safety always trumps. So if you ever see a question that says anything about human safety, that's probably your answer. They'll always value that above everything else. Physical assets also include, in their definition, people, buildings, systems, and data, physical things that you can touch. Threats like unauthorized access, disasters, man-made, natural, that's all going to be in this part. All right, perimeter defenses. Perimeter, keeping, it's the outside. A good physical security design would use a layered approach. So you'd have the perimeter, and then you'd have the entrance potentially, and then you'd have office spaces within those entrances, and then maybe you'd have a data center or closets inside of that. So it's a layered defense. Perimeter is the outside, the furthest out. Defense in depth is definitely, that's what I just essentially just explained. Fences, doors, walls, locks, those are all things. Fences, it depends on why you put a fence in. Some fences are nothing more than deterrents. They're very easy to get through or get over. Then there's also fences that are truly designed to keep people out. And you've seen the difference between them. If you go to a prison, those fences look a lot different than ones in in my neighborhood to keep pedestrians from just walking across your yard. Different purposes, different types. Most of the time, fences are used if you've got essentially deterrent fences work really good if you want to steer people somewhere, right? Ingress meaning into a facility, egress meaning leaving. Those are all important things. You'll need to memorize the gates. There are different gate types. It's all part of a standard, ASTM F2200. That's the copy of the standard if you want to go to the link. Different types of vehicle gates. So class 1 would be something that you'd probably see maybe at my home. Class 2, maybe class 3 would be something you'd see in an industrial park, right? Or a parking garage. Class 4 are, those are high security facilities, airports, prisons, enterprise data centers, things like that would all probably have class 4 restricted access. And the gates, there's all types of gates now. I mean, I love those gates that come out of the ground that are, steel and concrete that there's nothing getting over. That would be, class 4 type of gate. Control points at the perimeter, keep people out. But know those 4 different classes of gates would be important. That's how not to do a gate. It's kind of fun when you do, look up security fails. If you just Google security fails, you can find all kinds of interesting things with that. Bollards, like I mentioned, keep vehicles out. Different bollards for different things. It depends on what kind of vehicle traffic you're sort of expecting too, and how the approaches are designed. Some approaches are curved approaches that don't require as thick of bollards maybe as a direct approach to the facility. Think of how vehicles come into and leave the facility. A lot of times you'll see bollards also in front of convenience stores because sometimes people get messed up with what the brake is and what the accelerator is, and you've seen pictures of people running their cars through convenience stores. Bollards would, if they're installed correctly, would probably prevent that from happening. This is an example. So this is actually a physical security assessment I did a while back, and you can see that there's some problems here. For one, there's nothing in front of that big propane tank with ice in front of it and a vehicle. So this is a highly an often traveled area. It's a parking lot, and you've got ice and you've got something highly flammable. So that's not a very good design. The second part of this poor design, there are actually more than that, but the second primary part of this poor design is those bollards are not sufficient to protect that electrical box. So again, I don't even know why you'd install those 2 bollards for that. But that's an example of really poor design. Lights, detective controls and deterrent controls. So detective meaning, you can detect something that's already there. They're not preventative controls. Or deterrent. Attackers typically at night, if that's their modus operandi, they'll go to places where it's not well lit or places where there's a lot of foliage that they can hide themselves. Light would be a good deterrent control there. It needs to be bright enough to illuminate whatever your desired field of vision is. Now that's determined on however you designed. There's no one set number. It really depends on what the purpose of the building is, depends on what your risk tolerance is, all kinds of things. But whatever field of vision you need, the area that you need to protect, it needs to be bright enough for that. Now, what you don't see enough organizations do is do nighttime walkthroughs of their facility. Most people do it daytime walkthroughs, but few people do it at night to actually see what an attacker would see at night. It's a good idea to do that. Fresnel lights are those ones that you see in like lighthouses, for ships and things. That's that same kind of concentric design. Those are Fresnel lenses. They light specific directions as opposed to, kind of spraying light all over the place. It's just very focused light. Light measurement, you'll need to know these. Lumens, amount of light per one candle. How much light does a candle produce? It's just a measurement of light. Foot candles is how many lumens in a square foot. And then lux is just the same sort of thing, but with a metric system. So 1 lux is 1 lumen per square meter as opposed to per square foot. Not necessarily something you need to memorize, but good to know, and I suppose you might see it on the exam. CCTV, so closed circuit television, detective devices, also good deterrent devices. People typically, if an attacker is any good, they'll scope out the place first, and probably avoid places where there are cameras. Don't use fake cameras because they're pretty easy. They're a lot easier to tell that they're fake than you think that they are. Normal light spectrum versus, having, so some cameras, older cameras that aren't infrared, older cameras would need to have that field of view, that light thing that we were talking about. Infrared cameras, it's not as important. And then there's a question here, are cloud-based or cloud-enabled surveillance cameras considered CCTV? By the definition of CCTV, no, they're not. CCTV is closed circuit, so it's within a physical location, that type of closed circuit. So anyway, that's CCTV. Infrared devices can see in the dark. That's why they don't need that light nearly as much. It's interesting how you still see CCD cameras, or you still see the older analog cameras in some banks, believe it or not, that they're still reporting to VHS tapes. I don't know how that happens. I don't know how you can get VHS tapes anymore. But infrared sees in the dark, older tube cameras, analog devices, typically you'd have to have adequate lighting in order to see things. Also, the quality was poor. A lot of times you'll see people put in cameras that they don't capture. The quality is terrible, or they're pointed in the wrong direction. Cameras are one of those things to check regularly, because oftentimes we are just using them as more of an investigative type of control. There's not somebody sitting there watching it all the time. So you won't know that the camera was pointing in the wrong direction, or you won't know that the quality of the camera was so terrible that you can't use it in an investigation unless you check it regularly. I've seen that happen so many times. Cameras use irises that act the same way as human irises. They let light in. More light, further control. Wide aperture, that's essentially what you'd use in lower light conditions. You can think of the irises, or you can think of the same things like a cat, right? At night, it gets really wide so they can see better at night. You shine a light in their eye and it gets really small, their pupil. Works the same way. All right, features that are important: pan, tilt, zoom, PTZ sometimes you call it. Sometimes it's just pan and tilt, but pan, tilt, zoom is probably better. Other types, fixed camera view, it just doesn't move. Auto scan is it moves back and forth potentially. And these are the displays. So the displays might pop different cameras on the display. Then you have multiplexing where you have 16, 30, 50 cameras displayed on a single display. Just different types of displays for viewing camera images. Fixed camera view, auto scan, or multiplexing. Magnetic tapes such as VHS, believe it or not, we still see them. But there's lots of different ways to back up your images from cameras. And that's really important. I've also seen a lot of times when people didn't have adequate storage for camera images. So either it was set to overwrite, so camera images, maybe even from just a few weeks ago, were overwritten. You find out that some event happened 3 weeks ago. Well, you don't have the camera images for that. So it's important to take all these things into account in your own design. CCD cameras use DVRs, NVRs for network backups, and a lot of people are going cloud-based now. That would be sort of a version, I guess, of an NVR, just not under CCTV. Yeah, there's the poor camera design So that one would be really easy to just reach out from under and unplug the camera. So don't do that. Another poor camera design. That's it. All right, locks, preventative physical security controls. These do prevent physical access. They're not going to do, they could deter, I suppose, but not going to probably detect anything. Used on doors, windows, prevent unauthorized physical access into something. All kinds of different keys, all kinds of different locks, mechanical, key locks, combination locks. Some are electronic. They use smart cards or magnetic stripe cards, contact cards, all kinds. They have different designs. But understanding these basics, I think, is what's really important for you and for the exam. Key locks require a physical key. It's what you'd expect, right? A key that fits into a slot typically. Keys, this is probably one of the least secure methods of physical protection because every lock can be picked. It just takes different skill, different time, different things, but every physical lock can be picked eventually. Keys can be shared, sometimes copied. You lose them a lot. Common type of key lock is the key tumbler lock. That's essentially a key and it's got tumblers or pins, and you set the pins correctly, and then you turn the lock, and that's a tumbler lock. You can replace that tumbler. The correct key lines up the pins. It's called the shear line, allowing that tumbler to then turn. So pins, shear line, tumbler, all important things to know for key locks. All right, incorrect keys will result in misaligned pins, so it'll jam the lock. You won't be able to turn the tumbler. That's how it works. Ward locks or warded locks, the key actually goes through channels, so there is no pins in a warded lock. If you think of a skeleton key, if you've ever seen a skeleton key, it's just got those ridges, or not really ridges, like cuts that fit into the channels, which are called wards, and if it fits, it'll turn. Spring locks is just a jamming mechanism. It's for where the door jamb, where the door meets the door jamb. It's supposed to prevent you from springing or, opening the door without the lock. The door may be closed, spring bolt exposed, deadbolt, rigid. You've seen deadbolts. If you flip them, it's not going back in unless you can turn that lock. Spring bolts, you can take a credit card sometimes and slide it in so that it pushes back into the door, and then get in that way. All kinds of designs to prevent against that stuff, but this is good enough again for the exam. The strike plate is what is the part in the door jamb that the spring bolt hits. Deadbolts, usually there's a cutout for the deadbolt to go through. These are examples. So on the left you see the deadbolt, the spring lock on the bottom. You see the tumbler lock on the top. You see the shear line, the driver pins, key pins, lock plug. You just get the pins lined up with the shear line, and it turns. The warded lock, the one on the bottom there, instead of any pins lining up, it's essentially the cuts in the key have to line up with the wards or the channels, and that's what opens that one. Lock picking. So lots of different techniques for lock picking. It's a whole science. It's cool to see people do that. I don't do it anymore. It does take practice, and you do want to keep up on it. But it's the art of opening the lock without a key. You see the pick and a tension wrench. Those are two common tools. You can buy a lock pick set. In some places, it is illegal to have a lock pick set on you. So just check to make sure that that's not wherever you live. But essentially, what you're trying to do is in this case, when the example you see there, you're trying to line up the pins with the shear line so that you can turn. Then you'll just continue kind of rattling through with the pick and the tension wrench. Another technique is using a shaved down key, so you don't have the ridges correct, but you've taken another key and kind of shaved it down. And what you're going to do is you're going to bump and sort of turn at the same time. And what you're trying to do is bump enough to where those pins jump, and as you're kind of putting tension and turning, they'll fall back in line with the shear line and allow you to open the key. That's what bumping is. All key locks can be picked or bumped. It's just how long and how much skill. Master and core keys, these are keys that are like privileged level keys, like having admin access to your physical keys or physical locks. Open any lock in a security zone of a building. The master key can open up anything. The core key allows you to remove the core, so you can see on the bottom that's a key that's removing the core from the lock. Core keys allow you to essentially change and disable locks. So those are two types of keys. Keep ultra light control, tight control. If you are relying on key locks to secure parts of your building that are maybe more sensitive than others, it's a good idea to regularly switch out cores, because you just don't know if somebody else lost a key, or even though they used to have do not duplicate on keys, people still duplicate keys. To prevent some exposure from that, regularly changing out cores on locks is a good idea. Combination locks, you've seen these. There's the twist kind of combinations. There's the traditional master lock. There's the other ones where you've got the just the rollers. Really weak. Can always be. There's all kinds of attacks against combination locks. Button or keypad locks. Those are combination locks where, oftentimes you can see the wear on the buttons that were used for that lock, and kind of at least figure out what the 4 numbers were that were used to get through that door. You can also, there's all kinds of techniques to get past these locks. That's why they're very weak. We cringe whenever we see them. So the button and keypad locks, you've seen those. You just push buttons, a series of buttons in the right order, and it'll open the door. Keypad locks work essentially the same way. They're those types of combination locks as well. Low security applications. These are nothing more than deterrent controls. These shouldn't be really considered effective preventative controls. Smart cards, you can see the chip. We've all got smart cards now, I think. My bank card is a smart card. It's got a little integrated chip on it, and that's what's being read when you do chip and pin, right? You insert this thing in the machine, and it powers up the card, activates the card, and validates that it's a valid active card. Smart cards, they have to have a computer circuit. So if you just think smart card, have to have a computer circuit. 2 different types of smart cards, contact and contactless. Contactless smart cards have to have a power source external that power it up, getting it close enough to a reader, whereas contact you have to insert into the device. So if you're in America and you're using chip and pin, and you have to put that machine in, that's a contact smart card. So it have to be inserted into the smart card reader. Contactless cards can be read wirelessly. One type is RFID cards with an RFID tags. The transponder is what communicates with it. So transponder, we hear transponder, that's transmit and respond. So it's kind of both ways. RFID tags are read by the RFID transceiver. Magnetic stripe cards are also typically cards that you have to swipe on something. They have to be read. They're contact cards. No integrated circuit, so a magnetic stripe card is not a smart card. Those are the basics about those types of cards. That's a swipe card with a swipe card reader. Other cards, common access card, an example. So this is DoD has what's called a common access card, which kind of has like everything on it. They use it for authentication, sign documents, get into the commissary. Everything with the common access card. It is a smart card, stores data on it, certificates to validate identity and all that. Uses the DoD's own internal PKI, and this is just kind of an example of what that one of those looks like. And they change. All right, tailgating, piggybacking, we talked about this. Tailgating is essentially walking in under somebody else's credentials. So you just tailgated, you just followed them in. Lots of different ways I've done this over the years. The favorite way in Minnesota, it works nice. Just, you sit in your car, you wait for somebody to come, that looks like they're going into the office. You go grab a box out of the back of your car And you walk up there. People in Minnesota are so nice. They always hold the door open for you. They feel really rude if they don't. You do that same type of attack in like New York, they'll knock the box out of your hand and laugh at you, right? So you also have to take into account kind of where you're at and who you're going after. Another way to get into buildings is, stand by the smoking area. When people come out for smoke breaks and then they go back in, they'll hold the door open for you too. There's one time where I actually was walking out of a law office, a client, and when I walked out, it was just an elevator lobby. There were two lawyers that were coming to go into that, and when I walked out of the door, I closed it behind me rather than hold it open for them, and they both called me assholes for that. So you got to get used to that if you're going to play by the rules sometimes. It makes you feel awkward, but, there's a reason why we do it. Not that kind of tailgating. That's a different kind of tailgating. Man traps, turnstiles, these are things that would prevent against tailgating and piggybacking. Man trap, like I mentioned, is usually it's two different controls. It's one authentication to get into the man trap, and it's another authentication, a different kind of authentication to get out of the man trap. All kinds of different designs. There's weight-based man traps. There's all kinds of stuff that you can do. The important thing to remember about man traps, preventative control, two doors, probably two different types of authentication, separate types of authentication. Turnstiles are just those things that you see turn. There's all kinds of different turnstiles too. My favorite ones are the ones that have the interlocking teeth, so they stand vertical. There's a top and a bottom, and there's teeth. There's fixed teeth, and then there's the turnstile itself, which kind of goes, around. That's a turnstile. There's electronic turnstiles, but essentially lets one person through every authentication. No more. That's, no less probably too. You don't want to have the authentication egress. If you do have authentication egress, meaning to get out of the building in case there's an emergency or fire, you want them to fail open. But really, really rare. Most places, the building codes won't allow you to put an egress authentication out of the building. Maybe a badge out, or maybe an authentication out of a server room is different, but in general, not in buildings. Contraband checks. So this is, usually there's a guard check or something somewhere to check things coming into the facility and or things going out of the facility. Those are contraband checks. Sometimes they're spot checks. Sometimes we check everything that anybody's carrying in, looking for like UPS, for instance. Back when I was in college, I did physical security for UPS, and we would check everybody that came out. And what we were looking for was anybody who was stealing anything, right? So that's just one example of a contraband check. Other times it's, we want to keep weapons out. We want to keep whatever. Motion detection, detectors and perimeter alarms. Different types of these, the ones that you need to know for the exam, ultrasonic and microwave motion detectors. They work a lot like Doppler radar. You send out a signal, and you expect the signal to come back. If the signal comes back, at a different time, so let's say it took 10 milliseconds for normally for a signal to come back, and now one comes back at 3. That's an indication that something got in the way of the Doppler radar or the microwave or the ultrasonic signal. That indicates that something moved. Something either moved in front of that or moved closer, or something moved. That would be a motion detection trigger. That's essentially how they work. Active sensors, they mean they're actively sending energy. There are also passive sensors that are essentially sitting there waiting for something. Photoelectric motion sensor sends a beam. You see these on your garage doors. Those are photoelectric sensors, and if you break the beam, it means that something happened. In case of a garage door, it would send the garage door back up. In case of physical security, it might make an alarm go off. Passive sensors are read-only devices. They just detect, energy, oftentimes infrared energy, body heat. Something changed in the environment, and the sensor picked up on it. but it's not actively sending out any sort of signal and waiting for something to come back. That's a passive sensor. There's the garage door. Those are, those are beam sensors, photoelectric sensors. Perimeter alarms, magnetic door, window alarms. We've seen these. A lot of times they're contact alarms. So as long as two pieces maintain contact, we're good. A circuit is flowing through it. Power is going through it. Very low power, but something is going through it. When you open the door, that contact no longer is maintained, and so the power stops flowing. Then it starts an alarm, triggers the alarm. Matching pairs of sensors on the wall can be used. Window door sensors working the same way can be used. Not often used in real high security areas because you can bypass these, but in general areas like exterior windows, doors, things like that, you'll see these a lot. They'll trigger also door prop alarm. So if the signal hasn't come, it'll allow people to go through it, certain doors, and then if it doesn't get back to contact again, that's an indication the door's being propped open. That's another way to sort of trigger an alarm with some of these. There's an example. So the one on the right is there's the two contacts. One would go in the door jamb, and another one would go into the door itself. As long as there's contact, it's good. And then you can see on the one on the garage door on the left, it's not actually maintaining contact, but it's close enough to maintain a current. All right, doors and windows. Attackers go through doors and windows before they go through walls. Typically, it depends. But the weakest link is, hollow core doors, gypsum walls, which is sheetrock, windows. These are reasons why we don't like sensitive equipment on outside doors or outside walls, because if an attacker knows that that's on an outside wall, sometimes that's an easier way to get into it versus having to go through multiple layers of defense. Door hinges should always face inward if you can. There are door hinges that are tamper-proof that allow you to not remove the pin to take the door off. But a lot of times if the door hinge faces outward and you don't have that, it's really easy to get into that door. Internal motion sensors. Never include mail slots. Mail slots are also a somewhat easy way. You'd be surprised at all the ways you can get into buildings. External facing emergency doors should be marked as emergency. They should be alarmed if you can. Some places, believe it or not, building code doesn't permit you to do that. But it should have a panic bar, should be alarmed. We should always know when somebody's going through an emergency door. Glass windows themselves are structurally weak, but there's all types of different glasses that you can use to make them less structurally weak. Bulletproof glass, explosive resistant glass, wire mesh glass. You've seen all these types of glasses before. My parents actually installed, I used to break into my own house when I was a kid, because if you know me, I lose stuff a lot and I forget stuff a lot. And so I was a latchkey kid, and so I'd come home from school and I'd always lose my key or forget it somewhere, forget it in the house when I left for school. So I'd always break into the house. And there were two ways I would break into the house. One would be the garage. I'd try to get through there. But the easier way would be to go to our three-season porch and break a window, reach in, open it, because I'd have enough time to go to the hardware store, get a new piece of glass and glaze it, put it back in before my parents got home. So I'd always do that. Well, one day my parents changed out that window, or changed out actually all the windows there with plexiglass, and I had no idea. And so I was so used to just going there, and I'd take a hammer and I'd just kind of bop it and break the window. Well, it was plexiglass, so that if you've ever hit plexiglass with a hammer, it shoots back pretty fast. So it actually shot back, and I was just being dumb, shot back and hit me in the eye. So not only did I not get in the door because of the glass, I also ended up with a black eye and got grounded. So anyway, story. Other glass alternatives: polycarbonate glass, Lexan, acrylic glass, plexiglass. Those are all good, different, varied strengths of glass. But some glass is really, really difficult to get through. And so just take that into account as you're designing your own. Walls, floors, ceilings, these are all other ways to get into places. We always want slab to slab, so that means from the concrete to the next floor for any high secure area like data centers. It's really easy. We have a guy here, Matt Finley, who always climbs through walls to go from one office to another. So if you end up locking yourself out of your office, you just get Matt and he'll crawl through the ceiling for you. But the slab to slab prevents that from happening. Raised floors, drop ceilings, same kind of thing. If it's a raised floor, which is common, make sure you've got some protection. The raised floor maybe stops at the perimeter of the data center versus going out into other parts of the building. Any wall protecting secure perimeter, internal, external, strong enough to resist cutting. Sheetrock is really easy to get through. Walls have to have the appropriate fire rating, obviously, but you'll check with building code if you're actually building a building or designing it. Otherwise, your general contractor, your GC will know all that stuff. Guards, dynamic control, expensive, very effective if they're trained well. Not only are they a good deterrent control, but a good preventative control, a good detective control. I mean, it's just kind of an all-round good control. Aid in inspection. You can have them watching CCTVs, all kinds of things, making random rounds of the facility. A pseudo guard, or mall copish kind of person, is an unarmed security guard. Not to take anything away from them. I've done both of these jobs, pseudo guard and armed guard, and it's not a glorious job. It's really kind of a pain. But anyway, guards are great. Complete, clear. They need to be highly, at least not highly, but well trained on what it is, because they're humans, right? And humans can be hacked just as easily as anything else, sometimes easier. Dogs, there's all kinds of things they would use dogs for, but there's a big legal liability around using dogs, because if a dog inadvertently bites or kills somebody, you'll be open to lawsuits probably. But dogs are good for deterrent controls and also good detective controls. They used to use Maltese, little dogs, little nail ankle biters. Used to be great alarm dogs. So they used to use in palaces back in the day. And the alarm dogs, the Maltese, would alert the bigger dogs that, hey, there's something here. And so the bigger dogs would come. But it was kind of that, they used to use it, dogs like that. It's pretty cool. Liability is your biggest thing. There's my dog. You're probably scared of that. That's Vike. He's guarding our travel trailer. Yeah, he'll get you. He takes down deer. He doesn't look like much, but actually he's more than he looks. Site selection, design, and configuration. So much goes into it. Now, information security. Security always should be integrated as early into the process as possible. It's really, really difficult to move a building. It's really, really difficult to redesign a building if you didn't do it right from the beginning. So this is really important. Physical security, site selection, design, and configuration. How are you going to take this green field and turn it into something that's going to be secure for you? You have to take into account so many different things. So site selection process is where you start. The land, the data center, whatever you're going to be putting there, really important. Topography has to be taken into account. There's all kinds of really cool designs on how you can take the topography, the natural topography of a landscape, and use it to your advantage for security. So look for things like that. Steering people to, building things into hills, building things into mountains. Those are all good, topographical kind of things. Utility reliability is always going to be really important. In some places of the country, utility reliability is terrible. New York City is terrible. In those types of places, you'll need to have some accounting for what are we going to do when power goes out, because it's going to go out. Having UPSs in place, generators if you're expecting longer periods of outage, all really important in your physical security design, in your consideration for what you're going to do. Crime rate is really important. All kinds of places you can find crime rate. The sad thing about the crime rate reporting in the United States is it's not consistent. Some law enforcement agencies report crime better than others. So just be careful a little bit. Sometimes it makes sense to go and actually talk to law enforcement or the law enforcement agency in a site that you're considering, because the data you find may not be all that great. Two considerations here, not just there's violent crimes, right? Protecting the safety of your employees, but then you've also got, the theft and things like that to account for. So low crime rates, awesome, whatever. Site design and configuration issues, data centers, we don't want to mark them. You don't want to let people know that, hey, I got real sensitive stuff here, come and steal it. Where, some of the places that I've worked, big banks, you would never know that their data center was there. You would never know that a data center was in the middle of downtown whatever. You would never know it. You don't see any evidence. So not only is site marking with signs important to consider, but also where you put your generators. If you see a whole row of big diesel generators, that's probably a good indication that there's something that requires that there, like a data center. Just think of things like that. Those are all really important considerations in site marking. Try to draw as little attention to yourself as possible. I know that there's a saying, there's no security in obscurity. There actually is a little bit more in physical security. Shared tenancy, adjacent buildings. My God, we're going over, but sorry, a lot of data. We're getting there, promise. Shared tenancy and adjacent buildings, also considerations. If I'm building or locating next to a strip club or a liquor store, I expect a different type of cross traffic than, in an industrial park potentially, or an office park where it's all just office buildings. Those things all have to be taken into account. It's not that I wouldn't put my building next to a liquor store per se, but I'd have other controls in place. I would it would justify, probably some exterior cameras. It would justify different types of locks. Those things are all really important. In shared tenancy, the biggest place to attack is either an adjacent tenant. So go through, they may not have the same physical security considerations you do. You go in through there and then, go through a common wall, go over a common wall. There's all kinds of ways where you have to take into account other tenants. There's also, shared demarcation points, usually in the basement where you've got multiple circuits coming into the building and they're all being divvied up from one central location. That's another great place to attack. So take those things into account as you're building your own, physical location and such. Shared demarc, there you go. There's your shared demarc. Demarc, just demarcation point. It's where the ISP's circuits come in and where they get distributed from there. I've seen a lot of insecurity, even in downtown Minneapolis, some really nice Class A office buildings that just have terrible demarcation security. So take those things into account. System defenses, last line of defense, defense in depth, having multiple layers of defense, making it more difficult. It's not that you can you're probably not going to prevent a determined, skilled attacker from getting at what they want to get at, but you want to make it more difficult enough and noisy enough to where some detective control will trigger and you can stop it before it gets all the way through or all happens. Asset tracking, you can't protect what you don't know you have, so having things like serial numbers, model numbers, all those things, in case somebody steals it, in case there is a disaster, how are you going to replace it? Having been able to file insurance claims based on real data assets is going to be really important. Port controls, so that's switches. A lot of times you'll see people with active switch ports in conference rooms, in meeting rooms, in common areas, waiting rooms. Those are all physical security considerations. Where those ports connect to, whether those ports actually need to be active or not. We've been to multiple hospitals where they have an MRI truck or whatever that pulls up because those are so expensive that some of the rural hospitals will share those with each other. Well, they have to hook up to something, so they'll hook up to power and they'll hook up the data, and a lot of times those data jacks will be left on all the time. So when that truck's not there, it's a real easy entry into a network, a hospital's network, because they didn't turn the port off. So things like that are really, really important. Also, USB drives, plugging those things in wherever you want to, dropping them so other people will plug them in, all ways to get in. Physically disabling ports is the best way, so just removing the port altogether versus relying on somebody to configure your switch to turn it off. All really important stuff. Tape and drive encryption. This is a physical security. So the rule of thumb around encryption at rest, or actually any encryption, is if I can't ensure the physical security of something, encrypt it. So the physical security might be a drive, might be a tape, might be something mobile. If I've got things pretty well locked up, like in a data center, I could justify potentially not encrypting data at rest. Same with data inside of a facility. If I control the physical security of the facility, there's less of a need for encryption of data and transfer within that facility, because chances are somebody's not going to tap into the data flow. I control the switches, things like that. But I lose physical security of the media when it goes to the internet, when it goes to ISPs. That's when you have to put, that's when encryption should be a very strong consideration. So here, drive, tape encryption for data at rest, because those things move. Those things are mobile. It's easy to lose control of those things. That's a bad thing. Whole disk encryption, obviously on a mobile device, we used to get away some people would try to get away with just partition encryption, or not only have whole disk encryption, but whole disk encryption with pre-boot authentication is another must-have. Disk encryption and decryption, if it happens in this used to be a bigger consideration when we had more problems with CPU overhead for encryption, but now it's 3-4%, so it's not even noticeable for most people. When it was more noticeable, if you offloaded that onto hardware, a dedicated chip, it would go faster and you'd have better performance. But anyway, these are all important things for drive and tape encryption, media and storage. In transportation, backup data, store it off-site. And it's the same thing if I've got backup data electronic. It's just a different sort of off-site, right? Make sure that any incident, any natural threat or physical threat that happens to the primary data cannot affect the backup data, right? So that's why air gapping, is really important to protect against ransomware. That's why we take, physical data physically away, because if something destroyed my building, I don't want it to destroy my data too, right? So those things are all really important. Where you're storing your data, make sure you know where it's being stored. Is it being stored by somebody who's insured, somebody who's trained, somebody who's bonded to take that data? All kinds of things like that. Rarely are people using, tape backups anymore. I mean, some people are, but for tape backups, you have to take into account, environmentals for the storage facility and all things like that, physical access into the storage facility, checkout procedures, check-in procedures for data, stuff like that. This applies more to that than it does the electronic storage. But conceptually, any disaster that affects the production site, you can't allow it to affect your backup site as well. Media cleaning and destruction, we've talked a little bit about this before. Just throwing away media is it's not the way to do it. Physical destruction is the best way to get rid of data, whether it be remnant data on a drive or physical paper data in manila folders. Shred it, destroy it, all really, really important. You walk through any facility and do an audit sometime of if your facility has secure data destruction bins and recycle bins, or just recycle bins, go through the recycle bins sometime. Just do an audit and see what kind of data people are throwing away in paper files. And I think in most cases, you'll be surprised. Shred that stuff, get rid of that stuff that way. All right, environmental controls. Sorry, I'm going over late, but man, I'm going fast. Got to get through this. Designed to provide a safe environment for personnel. Safety is always going to come first. And equipment. So there are certain environmental constraints and controls that need to be in place for equipment to operate for as long as it should, and at the, it's sort of the capacity that it should. So things to take into account, certainly power. You have to have adequate power, stable power, protection against power outages, brownouts, all that stuff. HVAC, having the right heat, ventilation, having the right cooling, all those things are very important. Fire safety, obviously very important. Those are the three main types of environmental controls that will be on the test. Electricity is the number one thing to go out, I guess, in general. Number one disruption to business in data centers is electricity. So reliable electricity obviously is very critical. Most people, it's crazy how things have changed so much, but most people had data centers. Less people now have data centers than they used to. But having the reliable electricity for a data center, maybe if you're auditing a data center where you've got data stored, this would come into play more too. Big priority. So you'll have to memorize this. This is really important. It'll be on the exam. I've seen it talked about so many times. Knowing the different types of electrical faults is going to be important. Blackouts, prolonged loss of power. So power out for a long time, that's a blackout. Prolonged low voltage, so it's just running below what it's supposed to for a long period of time, brownout. Fault, short loss of power, right? It's the lights blink quick. That probably a surge, maybe it's a sag, but maybe probably a fault. Surge, prolonged high voltage, those are dangerous. Usually you'll trip circuits then. Circuits will trip and you'll have no power, but it'll be because of a surge. Same with spikes, and then sags, temporary low voltage. So memorizing this is going to be important. Please do it. All right. Protections against power failures, surge protectors, just what they do. They protect against surge. Power surge, and protect the electrical equipment. They'll probably trip a circuit or something within the surge protector to protect your device or server or whatever you have connected to it. There's really no other power conditioning really in a surge protector. Uninterruptible power supplies, backup power, if you have a power outage, blackouts, not for blackouts. UPS would be more for short power outages, brownouts. There is power conditioning that happens in a UPS. Clean power, surges, spikes, other forms of electrical faults, not for those blackouts, long periods. You would have usually a transfer to a generator if you want to protect against that. Different types of, two main types of transfers. You got the automatic transfer and a manual transfer, so you'll have to manually transfer power from one to the other. That's from going from your UPS or your normal power supply to a generator for a blackout. Generators, long periods of time. You need to have enough time, usually on your UPS, for your generator to come on and for power to switch. You also want to have enough fuel supply for an extended period of outage, depending upon other factors about the site that you're at. Having some form of refueling. It'll always be critical infrastructure. It'll always be hospitals who get their fuel first if you're doing like diesel or any fuel supply really. But there are some fuel supplies that are just kind of constantly run, like natural gas is maybe a better choice in some cases. Anyway, all kinds of different generators. This is what they're used for. Need to test them regularly, need to be serviced regularly. Last time to find out that a generator isn't working is when you need it. EMI, electromagnetic interference, is, we'll get into this more too next week when we talk about crosstalk. When network cables aren't sufficiently shielded and they're too close to each other, you'll get this crosstalk. That comes from EMI. Used to get them on phones, old phones. When you talk, I don't know if you remember, when you talk to somebody on a phone, you'd hear somebody else's conversation. That was crosstalk. The cables were too close and they weren't shielded, so you got that crosstalk thing. Never route power cables close to network cables. I have a whole bunch of stories there, but I can't tell you now because I'm way late. HVAC, reasonable temperature, reasonable humidity or within a range, closed loop recirculating treated air, reducing dust, airborne contaminants. There's all types of different HVAC systems that you can use. Positive pressure and drains is really important in these scenarios. Positive pressure would mean that things flow out versus things being sucked into the data center. That's to protect against contaminants if there's some sort of break. And same with drains. Having positive pressure drains allows things to drain out of the building versus draining back into or inhaled into the building. Important parts of HVAC design. Different data center temperature recommendations. So there is no one set of data center recommendations for you. It depends on who you ask. And this is, I think, just important to sort of know, but it's not going to be testable. I think it's just interesting information, the different temperature recommendations and the optimals. Heat levels or humidity levels, 40 to 55% are recommended. When things get too dry, you get static electricity. When things get too wet, you get corrosion. So keeping it within that range is really important. Common recommended set point for temperature, 68 to 77, whatever. All kinds of different sources. But remember about humidity, too much water in the air leads to corrosion. Not enough water in the air leads to static electricity, both of which are bad for electronics. That's what I just said. So there's your static and corrosion things about too much water in the air, meaning high humidity, too little water in the air, low humidity. This is what you get. Airborne contaminants, all types of VESDA systems and things that essentially monitor the air in a data center or somewhere for contaminants. There's all kinds of different ways to do it. Things that contribute to more dust and contamination in certain areas. Bringing a server in its cardboard box and then deboxing it in the data center. That's a bad thing, right? Because you introduce more airborne contamination. Lots of things that contaminants do. They gum up fans, which are moving parts meant to keep servers and things cool. So they often create overheating. All kinds of bad things happen with airborne contaminants. Heat, flame, and smoke detectors. 3 methods to detect fire: heat, flame, and smoke. Typically, you get an alert locally and then potentially something centrally monitored and potentially even something out to the fire department, the local fire department. Audible alarm and flashing lights are important. The reason why both are important is some people can't see, some people can't hear. Everybody needs to know that there's a fire. So having both of those is really important in any farm or any fire system. Heat detectors, so they just monitor a certain temperature. If a temperature exceeds a certain threshold within a specific period of time, it'll trigger. So, temperature raised 10, 15 degrees in 3 minutes, that's not normal, and those things will trigger a heat detector. That's how they work. Smoke detectors, 2 different types of smoke detectors, typically ionization and photoelectric. Ionization, just a small radioactive force or source, a small electrical charge, and if that charge changes, and it would change because smoke, got on it, essentially, that would trigger the alarm. The other one, the photoelectric sensors, is the same type of photoelectric we talked about with preventative or detective control. It just sends a small charge, and when it receives light or there's something different in that, it'll also trigger. So dust can set off smoke detectors, which would be bad in your server room. Flame detectors, infrared light, ultraviolet light, big fluctuations in light, that flicker. That's what those will detect, and that's what will make those trigger. The thing about flame detectors, though, that makes them a little less effective, and there's nothing wrong with using a combination of these, but flame detectors, they have to have line of sight. They may not pick up a flame happening on the other side of a wall, other side of a storage rack, something like that. So that's important about flame detectors. Safety training and awareness. Train people. Awareness Go through drills. Fire drills are still important. I know people don't like to do fire drills, but they're important. People need to know how to get out of the building. People need to know who to talk to. Is there a safety warden for the floor who coordinates things? Where are people going to assemble when they get out of the building? Who's going to account for people to make sure that everybody did get out of the building? Those are all really important things, and having that training and awareness stuff is important. Also, just for physical security and safety issues, not allowing people to come in the door. Don't hold the door open for people. It may be uncomfortable, but there's a reason why we do it. Whatever. Having those evacuation routes plotted, you'll see those in many buildings. You usually see them by the stairwells or elevator bays, just how to get out of the building. It's always a good idea to look at that. Make sure you have that. Make sure that people know about it. That's all part of your safety training and awareness. Evacuation rules and procedures. This becomes important. You'll see this in disaster recovery planning and probably business continuity planning and probably occupant emergency planning. A safety warden and meeting point leader. Safety warden just coordinates everything to get out of the building, right? They ensure that people get out. They coordinate drills, things like that. The meeting point leader essentially counts everybody. Did everybody get here that we expected to get here? Both of those people are very important. You do have to account for handicaps, egress, all that stuff. And it seems obvious to some people, to me anyway, to not use the elevator during a fire, but you're not. All that stuff is important. This is now getting into another, we're almost done, guys, 14 slides left. This is really important for memorization for the test as well. ABCD fires, different types of fire suppression put out different types of fire. If you use the wrong suppression on the wrong type of fire, it could get worse than better. So the different agents require different fires require different suppression. Class K fires, so it's not ABCD, there's a Class K, which is wet chemicals, and it's used for kitchen fires. A lot of times you'll find Class K in homes in general, RVs, things like that. But knowing that Class A is kitchen fires and it's wet chemicals is what you need on this page. You'll need to memorize this. This is going to be really important. So fire classification of A, that's just your normal kind of paper, wood stuff. Some rubber, plastics, things like that. Water puts that out. Dry powder, halon, those all put it out. You'll see on the fire extinguisher itself or whatever mechanism you're using, these letters, right? The triangle A, the square B, the circle D, or C, and then the D for metals. Memorizing this is going to be important. Knowing the ABCs, what fires they're used for, knowing the type of extinguisher will also be important. So this will be something to memorize, so mark this one down. Types of suppression agents, always consult. Yeah, obviously, if you ever have questions about fire, you don't go to a book. You go to talk to the fire department. That's what they're there for. So if you have questions about fire stuff, go talk to. And that's another tip for the exam too. If you ever have an option to talk to a specialist, go talk to the specialist. That'll be your answer. So go talk to the fire department if you have questions about how to protect yourself properly from fires, even how to run drills. So the suppressant agents, one of four methods. You remove the supply of fuel. I always think of fuel as being oxygen as being one of those fuels, but because it's always a mixture, but there are these four. Drop the temperature, remove oxygen, remove the fuel, or create some type of chemical reaction to where the fire can't continue to combust. Those are your four ways. Water does this, right? Lowers the temperature. It'll also suppress, it'll remove fuel a little bit and remove oxygen a little bit. But the main thing it does is it lowers the temperature below that ignition point. That's what water's used for. Never use water on electrical power. You never use water on really, oil and gas, and use it on your type A fires, basically. Soda acid, the old giant brass fire extinguishers, they also lower temperature, but they also create a foam. I think they can choke the fire out a little bit. This is what those used to look like. They're kind of cool. Don't see many of them anymore. Dry powder, just It works by, it also lowers the temperature, but this truly is more of a smothering thing. It starves it of oxygen. That's what dry powder is used for. Use this in metal fires. That's its primary purpose. But you can use this one in other fires as well. CO2. So CO2 is, if you smother a fire with CO2, you're also going to remove all the rest of the oxygen in the room. So this could be really dangerous for somebody who's in that room when it goes off. That's why we don't see this very often. We may see it in like some remote storage facility or something where there's just not people there. That might be a place to use CO2. It's very effective because it removes the oxygen and kills the fire, right away. People don't know when CO2 is in the building, so they'll just die. So really important to not use CO2 where there are going to be people. Halon and halon substitute. So halon is not really permitted anymore, but it creates a chemical reaction with the fire, which essentially stops the combustion. There are replacements now. The Montreal Accord in 1989 banned halon because of the ozone layer. It killed the ozone layer. So now you have to use substitutes. There was a time for a while where you could still use halon, kind of like a grandfather time, but it's not being produced anymore. There are some critical places where it's still being used, but you don't see it anymore. This is what you see now. Instead of halon, argon Fe13 FM200 is probably the most common one that I've seen is FM200 and Energen. Fe13, the newest, relatively safe, can be breathed up to 30%. It's probably not something I'd advise, but you could do it, according to the experts. Other halon replacements typically save 10 to 15% concentration, and then beyond that, you'll suffer some health consequences. But you've seen FM200. It's the big red things, big red tank, and then usually the balls, have that brass with holes in it. Sprinkler systems. Sprinkler systems are still the most common, even in data centers, believe it or not. Sprinkler systems are still the most common fire suppression system. Different types of sprinkler systems that will also be in the test. You've got wet pipe. So wet pipe means that the pipe is actually full of water. There's only one valve that's holding that thing back, and that's going to be the sprinkler head itself, right? So the sprinkler head, there's a small glass bulb, and different color bulbs mean that they melt at different temperatures. So you can actually look at one and see if it's red, and it's, I think, 165 or whatever the temperature is. But when they break, that just releases the water. The dangerous thing about wet pipe is that if it freezes, you're going to burst the pipe. So you don't want to use this in low temperature areas. It also doesn't give you any time. There's no time to react. If it goes, it goes. There's no okay, it goes, and then I got some time to double check. Those are the things about wet pipes. Plus, if I knock a sprinkler head, the water's coming out, and that's dangerous too. So wet pipe, red is 155. I don't think you have to memorize that, but those are the colors. If you look at the bulb on any sprinkler, you can see when it's going to melt, essentially, or break open. Most of them are red. And I don't think you need to memorize too much on this, but do know and memorize that wet pipe is what it is. Pre-action does give you some time. Combination wet, dry, or deluge systems, 2 separate triggers. So one, most commonly, there's no water in the pipe at all. So it's just air. So when these things go off, when the first action goes off, you hear that's the water pushing the air out. If you didn't already have an alarm or something, that's an indicator of crap. But first thing is it fills the pipe, and then there's another action that would actually open the valve and release the water. That's how pre-action. They give you some time to maybe deactivate the alarm system or do something before water just comes and floods out. This would be my favorite type of, if I were using sprinklers in a data center or something, this would be my favorite type. to use. You can also use this in cold areas because there's no water in the pipe. Portable fire extinguishers. They have the pass method, so pull the pin, aim low, squeeze the pin, sweep the fire. That's how you use a portable fire extinguisher. What most people do is just shoot it. But if you've been trained, this would be the right way to do it. And for those maybe safety wardens or certain people within your organization, it makes sense for them to get some training on how to use a portable fire extinguisher. You get more comfortable using it when you actually need it if you've already done it before. You're not so surprised by what discharges out of it. Holy mackerel. Sorry, guys. I'm only really late. All right, we left off on page 212 on the book. Monday, 5-4, we're going to get technical. Brad is leading the next class. He's going to get through it faster and probably better quality than I did. He's good at technicaling, and that'll be what we're doing. Yeah, that was a lot, and I appreciate you guys hanging in there and getting through it with me. We'll see you on Monday. Thanks.